Hey everyone! So, have you ever stopped to think about how your computer juggles all the different things you ask it to do at once? It's not magic, it's something called scheduling. And today, we're diving into one of the most famous algorithms out there, shortest job first. Now, the name sounds super simple, right? But trust me, it packs a crucial secret about efficiency and, yeah, a pretty major flaw. So, let's get right into it.
Okay, to really get this, let's imagine something totally non-computer related. Picture this, you're at a print shop. There's a line. The person in front of you needs a single one-page flyer printed. The person behind them, they've got a massive 100-page report. Who do you help first? I mean, it's a no-brainer, right? You knock out that one-page flyer in a few seconds. Why? Because that way, the most people are happy and the overall wait time for everyone goes down. And that super simple, intuitive idea, that's the heart and soul of shortest job first.
So, let's bring that back to your computer. In this analogy, the print shop is your CPU, the brain of the operation. And those jobs, the flyer and the report, those are called processes. Your operating system, whether it's Windows, Mac OS, whatever, is constantly playing the role of that print shop manager, or maybe a traffic cop, constantly deciding which process gets to use the CPU next. This whole procedure is called CPU scheduling, and it is absolutely critical for making your computer feel fast and responsive.
All right, so let's start with the basics. We're going to look at part one, the simple solution, which is called Non-Preemptive SJF. It's the most straightforward version, and it has one very simple rule.
Okay, so what does non-preemptive even mean? Well, it's pretty simple. No interruptions. Once the CPU gives a process the green light, that process runs all the way to completion. No cutting in line, no stopping at midway. Period. The scheduler's only job is to look at all the processes waiting in the queue and pick the one with the shortest burst time. And burst time is just a fancy way of saying the amount of time that process needs to do its work.
All right, enough theory. Let's put this thing to the test with a real example. So here we've got 4 processes, P1 through P4. You can see each one has an arrival time, that's when it shows up, and a burst time, which is how long it needs the CPU. So let's walk through this and see how our non-preemptive scheduler would handle this exact situation. Okay, let's build the Gantt chart for this. At time 0, nothing's happened yet, so the CPU is just sitting there, idle. But then, at time 1, boom! 2 processes arrive at the exact same time, P1 and P3. So the scheduler has a choice to make. It looks at their burst times. P1 needs 3 units of time, but P3 only needs 2. Well, the rule is shortest job first, so P3 wins. It gets the CPU.
So P3 starts at time 1 and runs for 2 units, which means it finishes up at time 3. Now, what's happened by then? Well, P1 is still waiting, and P2 has also arrived at time 2. So the scheduler has a new decision. P1 or P2. P1 needs 3 units of time, P2 needs 4. Again, shortest job first, so P1 gets to run next. It starts at time 3, runs for its 3 units, and finishes up at time 6. Easy enough, right?
Okay, now things get interesting. At time 6, P1 is done. Who's waiting? Well, P2 is still there, and now P4 has shown up at time 4. Let's check their burst times. Wait a minute, they're both 4. We have a tie. So what do? There has to be a tiebreaker rule, and in this case, it's simple. First come, first serve. We look at their arrival times. P2 arrived at time 2, P4 arrived at time 4, so P2 was here first. It gets the CPU. P2 runs for its 4 units, finishing at time 10. And now, the only one left is poor P4, so it runs last, finishing everything up at time 14.
So, that's the whole sequence. But, was it any good? To figure that out, we need to do some calculations. This table breaks it all down. We can calculate the completion time, the turnaround time, but the metric we really care about, the one that tells us how efficient this was, is the waiting time. That's literally how long each process was just sitting around in the ready queue, waiting for its turn.
And if you add up all the waiting times and divide by the number of processes, you get 3.0. The average waiting time is 3.0. Now I want you to burn that number into your brain. Just remember, 3.0. Is that a good number? Is it bad? Well, we can't really know until we have something to compare it to, and that's coming up next.
All right, part 2. I'm calling this the preemption plot twist. Because, 3.0 doesn't sound too bad, but this simple no interruptions approach has a really big, kind of fatal flaw. And this is where things get really cool.
So, let me ask you this. What happens if a really long job, say a 20-minute video render, is running on the CPU, and then suddenly a tiny super urgent job shows up that only needs 1 second? With our current no interruptions rule, that little 1-second job has to wait in line for the entire 20 minutes. That
Doesn't really feel like shortest job first, does it? It kind of defeats the whole purpose. The solution to this problem has a name. It's called preemption, and it's exactly what it sounds like. It's the ability for the operating system to interrupt, or preempt, a currently running process, to say, hey, hold on a second, something more important just came up. When you apply this idea to shortest job first, it gets a special name. Shortest remaining time first, or SRTF. The rule is simple. If a new process arrives and its total burst time is less than the remaining time of the process that's currently running, the OS will swap them out.
Okay, so you know what we have to do now, right? Let's run a whole new simulation. But this time, we're doing it the preemptive way, with SRTF. Here's our new set of processes. Now, fair warning, this is going to get a little trickier. Why? Because with preemption, the scheduler can't just make a decision and forget about it. It has to reevaluate what's best every single time a new process shows up in the queue. Okay, let's trace this out. At time 0, P1 is the only one here, so it starts running. It runs for 1 unit of time. But then, at time 1, P2 arrives. The scheduler immediately wakes up and checks. P1 started with a burst time of 5, and it's run for 1 unit, so it has 4 units of time left. The new process, P2, needs a total of 3 units. Well, 3 is less than 4. So, preempt. The OS pauses P1 and immediately gives the CPU to the shorter job P2. So P2 runs, and it actually gets to run to completion because nothing shorter arrives to interrupt it. It runs for its full 3 units, from time 1 to time 4. Now, right at the moment it finishes, at time 4, P4 arrives. So the scheduler looks around. P2 is done. P1 is waiting with 4 units left. P3, which arrived at time 2, is also waiting with 4 units. And the brand new P4 only needs 1 unit. Well, 1 is definitely the shortest, so P4 gets to go. It jumps on the CPU at time 4, runs for its 1 unit, and it's done by time 5.
And look at that, another tie. Both P1 and P3 need 4 more units of time. So what's the rule? Same as before, first come, first serve. P1 arrived way back at time 0, P3 arrived at time 2, so P1 gets to go first. It finally gets to finish its remaining 4 units, running from time 5 to time 9. And that just leaves P3, which runs last, finishing up the entire job at time 13.
Okay, let's crunch the numbers for this preemptive version. The interesting thing to look at here is P1. Its turnaround time, the total time from arrival to completion, is pretty high, 9 units. But that's because it was paused in the middle. The waiting time is what we're focused on, and you can see that 2 processes, P2 and P4, had a waiting time of 0. They got to run almost as soon as they arrived. That's the power of preemption. So what's the final score? The big number? The new average waiting time is 2.75. Remember the number from before? It was 3.0. So we went from 3.0 down to 2.75. It might not seem like a huge drop, but it's a definite improvement. All that extra work of interrupting and swapping processes actually paid off. It made the system more efficient by reducing the overall average wait time. So there you have it. Preemption is faster. SRTF gives us a better average waiting time. So it's the clear winner, right? We should just use this for everything? Well, not so fast. It's not that simple. Let's get to the final verdict on SJF.
Look, on paper, in a textbook, SJF and especially SRTF look perfect. In fact, it's been mathematically proven to be optimal, the absolute best algorithm for minimizing average waiting time. It also gives you amazing throughput. But, and this is a huge but, it has a couple of massive, real-world problems that keep it from being used everywhere. Let's talk about them.
The first big disadvantage is a problem called starvation. Imagine you have a big, important, long-running process waiting in line. But what if a never-ending stream of tiny little jobs keeps showing up? Every time our big process thinks it's its turn, another tiny job cuts in front of it, and another, and another. It's possible that our big process could wait indefinitely. It might never get to run. It's literally starved of CPU time, and that's a really, really bad thing in an operating system. Okay, let's wrap this all up. What are the key takeaways? First, SJF is all about picking the process with the shortest burst time. The non-preemptive version is simple. It just runs a process to completion. The preemptive version, SRTF, is more complex but more responsive because it can interrupt a process for an even shorter one. And while SJF is proven to be optimal for average waiting time, it comes with that dangerous risk of starvation. But honestly, the biggest, most fundamental problem of all is the one we've been ignoring this whole time. How in the world does the operating system know the burst time of a process in advance? The honest answer is, it can't. You can't know how long something will take until you actually do it. And that massive prediction problem is why pure shortest job first is more of a beautiful theory, an important benchmark that other algorithms are measured against, rather than something you'll find running in your computer today.